can we be sure that's turned on? The
I think it's on. Yes, it's. Yeah.
Okay. Our next speaker is Jian Qing and Jian Qing Shi, and he's going to be talking about generalized Gaussian process functional regression models.
Okay, so it's my turn now. So today I'm going to talk about the generalized Gaussian process functional regression model. So this is a joint work with Dr. Wang. So first of all, I will discuss a simple motivating example and say a few words about the Gaussian process regression model, and then discuss the Gaussian process functional regression model. This is for a continuous functional response variable, and the generalized GPFR is for functional categorical data. And then so I'll show you some results and give you some comments. Okay, this is a motivating example. So here, basically, we wanted to model a standing up maneuver. So our response variable yt is the position of body center. So usually we know it's not very easy to determine the position of body center, and actually we just don't know where our body center is. And this usually it's quite expensive, and it's not easy to find it. And then so in biomechanics, so usually they measure, they get the measurement for some other variables. So here I list some variables. Actually it can be collected from those sensors. So those are the position of those sensors, which attached to the different parts of human body. And so in our project there are total 30 variables. So our objective is you want to use the input variable of those xt to predict this yt. Now because this is a standing up maneuver, so all those yt and xt, they are functional data. Okay, this is some data. So that is each curve is corresponding to one standing up, and so that one is the response variable, and so that's basically in the vertical direction, and this is one input variable. So we can find there's a lot of noise in these input variables. Okay, so if we wanted to determine the exact the position of body center, so this is a continuous functional response. And but in practice, quite often we just wanted to know what actually the phase of those of our body center. So in this case, so this is categorical data. So what is our data? So actually we collect the data from many replications of the experiment. So for M subject or for M standing up, so we observed some functional response yt and zt. So at the time, at a point I from 1 to nm, and at the same time, and also at the same time point, we have got the data for those functional covariates. We also have some scalar covariates. So for example, the weight, height, or gender for those subjects. Okay, so now our problem is how to find the f. So usually this f is unknown, or we want to this f is non-parametric. This is because you can just think about if this y is the position of body center, and those x1, x2, xq is some force from your feet or from your bottom, and then so at the moment we just don't know. So the physical meaning, physical relationship between those y m and x1, xq, t. Now, so here, so I think this is here. If the q is the dimension of all those functional covariates. So usually if q is small, for example, if less than 3, so actually we can use any yeah, I mean, there's conventional non-parametric method. But if Q is larger than 3, I think as yeah, Professor Wang mentioned this morning, yeah, this is a difficult problem for our statistician. And I think a neural network model at the moment might be the most popular model used in engineering. And yeah, we think a Gaussian process regression model is an alternative way. So basically, the neural network model is a local approximation model, and the Gaussian process regression model is a global approximation model. So at least in some circumstances, yeah, the Gaussian process regression model is better than neural network model. And so today I will discuss the generalized GPFR model. So this is for some functional categorical data. Okay, so before I discuss this Gaussian process functional regression model, I want to say a few words about Gaussian process regression model. I think Mingyuan had mentioned this one in his talk on Tuesday afternoon. So basically, yeah, so Y is also a response curve, X is also a functional, this is a covariate. So we wanted to find F, yeah, so F is unknown. Okay, so the idea of Gaussian process regression model, actually we just define this F by this Gaussian process in a functional space. Okay, so now I think I just skip the details. So the feature of this model, so first of all, this X could be a large dimensional. Now, at least if Q is 10, that's definitely not any problem. And so it's also easy to calculate the prediction. So F hat GP, so this is actually the posterior mean for this one, and so this is the formula. And this is a non-parametric model. This is because basically this Gaussian process regression model can be used to fit almost any curve with any shape, of course, and some regularity condition. And select a kernel covariance function K here is basically equivalent to select a basis function in some conventional non-parametric method. Naturally, this has mentioned by Grasshopper in 30 years ago. I think I just skip the previous slides. I just show you some results here. Here, basically, it says if we use a Gaussian process regression model, so this is F hat GP, is the prediction based on the Gaussian process regression model. And then, so we can construct a reproducing kernel in a Hilbert space for this P1, and then, so, and there's some condition, so they actually is equivalent. So this is, I want to give you an example. So actually, a Gaussian process regression model with this particular covariance, a kernel covariance function, this is equivalent to a linear piecewise approximation when the number of nodes tend to infinite. Okay, so now I start to discuss a Gaussian process functional regression model for repeated curves. And actually, from this slide, you can find that we actually borrowed the idea from Rice and Silverman's 1991 JSSB paper. So in their paper, so they basically want to model both mean and the covariance structure. But here we can just think about this T is just a one-dimensional functional covariate. Yeah, and so here, since we found that actually, if we just replace this tau mt by this tau mx, and so that means actually this model can be used to model the regression relationship between this y and this set of functional covariates. Now, why we replace this tau mt by this one? This is because if we just focus on this part, so usually when this Q is large, so most of non-parametric method it's just have problem. Yeah, okay. Okay, so here, so our tau mx we just simply defined by a Gaussian process regression model linked to a kernel covariance function. And actually, this mu mt, because this mu mt is just dependent on a one-dimensional covariate t here, so actually we can use any type of non-parametric model. No, so in our paper, we just use this one. This is just the functional linear regression model used in Ramsey and Silverman's book. Okay, so here we said that the regression relationship between yt and x1 to xqt is mainly modeled by this Gaussian process regression model, and then so the prediction, at a new. Now, since in our project, our main purpose is to calculate the prediction. So prediction including two parts. So this is the main part. This is the main part. Actually, it's so this is just the usual way. We estimate this main curves from those repeated curves, and so this one actually it's the most important part in our model. I think it's better to show you the next slides. Okay, so here in this figure, okay, the blue one, the solid one, is actually the mean, that mu m hat. And so the red one, red dashed curve, is the actually ymt. So here, this blue one, this is just a usual mean part. So we just say lend this blue part by borrowing information from all from the data collected from all the subjects. And here the most important part is the second part. So the difference between the red one and the blue one is just actually it's a residual. And then we use a Gaussian process regression model to model this residual. And then in my so this part is the part corresponding to this Gaussian process regression model, and then we use this one to improve the prediction. Now, because we can combine the information from all subjects, all other subjects, and the data collected for those particular subject, and so at least so we our simulation study and simulate shows that this improves the fitting and the prediction quite a lot. Okay, so now I discuss the generalized Gaussian process functional regression model. Now, actually, this part is not very difficult. This is a natural extension from the previous Gaussian process functional regression model. So here, previously we said the yt is a continuous curve, but here zt, it's maybe a categorical response variable, so it has not a normal distribution. Here we just simply assume it's from a exponential family. And then we also have those two types of covariates. So one is a set of functional covariates, and the another is those scalar covariates. So now our problem is, okay, so for any distribution from this exponential family, so if G is a link function, so of the transformation of this mean, so usually now for a generalized linear regression model, this one can be modeled by, for example, x beta. But here, since we wanted to find a non-parametric model, so now the problem is how to find this Fm. So this is our idea. So here we just simply say, okay, so replace this Fm by the GPFR model I just mentioned. So if this torque x is given, and so this is corresponding to the mean part, and this tau x is corresponding to a Gaussian process regression part. And so here, as it's the same as the Gaussian process regression model. So regression relationship between this zt and this x1 xqt is mainly modeled by the second part. Model learning so means we tried to now so here basically beta t is approximated by, for example, a B-spline, and so for a kernel covariance function, since it's involved some unknown parameters, so we need first step is we need to learn this model structure, and yeah, this is not very easy because it involved a multidimensional integration. So at the moment we use a Laplace approximation. It seems okay, although it's yeah, it converges seems not very fast. Okay. So here, so that's the prediction. So prediction also including two parts. So this part is corresponding to, I said, is a common mean. So basically, yeah, to estimate this part, we needed to borrow the information from other subjects. And the another part is corresponding to this tau star. So this tau star, so this is mainly dependent on the data observed from this particular subject. Now, if, for example, for a completely new subject, we haven't observed any data, so we can only use this part. But yeah, if we have observed some data for this subject, actually we can improve this prediction, yeah, quite a lot. Okay. Okay, I think I almost finished it. So here, this is just a simulation data. So here for the different yeah, sample size, so this blue one, I think, is the blue one is the true underlying the latent variable of this y and t, and so the red one is the predicted one. So we can find it works quite well. And so this is the example I showed you at the beginning. So now actually in this example, so we have the 30 input variables, but at the moment we only use 8 of them. Yeah. And so we have got the data from 40 replications. And so next slide show you some results. So the blue one is just the data. Blue one is the data collected from this particular subject. And so basically the red one, the blue one is just, yeah, we only take the observation from here to here. So basically the red one here is just the fitted values, and in the other part is a prediction. Yeah. So we can find this, yeah, I mean actually our model, yeah, I mean give a quite a good result. Okay, I think this is almost my last slide. So we haven't finished this project yet, but at the moment, we mainly focus on studying the static properties. Actually, there are two parts in the inference. So first part is about the model learning. So this is actually not very difficult. The difficult part is how to consider the posterior consistency and information consistency for those predictor functional response. This is because basically we borrow we combine the two types of information. So the error bound or the consistency depend on the different type of kernel covariance function. It's also dependent on the total sample size, also depend on the sample size for each individual subject. Yeah. And at the moment we use the Laplace approximation. Yeah, it seems okay, but we hope we can find some more efficient algorithm. And so for the model selection part, so now I just mentioned if our Q could be quite large. For example, 10, 20 is okay. But if this Q is very large or even is larger than the sample size n, this actually is a problem. So I think Mingyuan mentioned this problem in his talk. Okay, and also we're also interested in some dynamic modeling. Okay, finally I want to thank some of my other collaborators. And so all the references I mentioned in this talk can be found in my website. I think that's all for my talk. Thank you.
we have time for a few questions. Anything? Okay. Quiet bunch. Okay, well, why don't we thank Jian Qing again.